So we talked about having all of this binding energy that's holding the nucleus together once it's created into its nucleus from its constituent components of protons and neutrons. Now we're going to see how much binding energy there is if I was to separate it per nucleus, and we're going to graph that. And that's what this graph is, a very important graph. And you will see that it is the mass number divided by, with the binding energy per nucleon on the vertical axis, and the mass number, which you know is neutrons and protons, on this axis. So I'll draw a picture, and I'm going to simplify it. I'm not going to put that little deal here. I'm going to go like this. So there's mine, and I'll stop where you can see it. Can you see it yet? Right there. Okay. So now I'm going to put an axis here. And here's binding energy per nucleon, which means binding energy per neutron and proton, however many there were. And then this is the mass number. So this is the total number of protons and neutrons. And I come way down here, and here's 0. And I'm going to come way, way over here, and I'm going to put 250. So if I had 92 uranium-235, it would be way over here. So what we can see is, as I start creating certain elements, hydrogen being way down here, helium, that the binding energy is going up as these elements are created until it actually reaches a peak right here. This peak is actually iron 56. Pretty cool. So what is actually cool now, as I continue to add protons and neutrons into the nucleus and go this way, after I get past iron 56, look what's happening to the binding energy per nucleon. It's actually coming down, which if I was to come out here and look at these really heavy isotopes that we deal with, uranium and plutonium, I'm dealing with a low binding energy per nucleon. Anywhere past iron 56 is where fission becomes possible. Anything before that is where fusion is possible. I didn't say it was possible on Earth, but it's possible. So this will become an area of concern, because essentially another way of saying that is the binding energy is getting less and less and less and less as I get a heavier and heavier and heavier isotope, and it's going to be easier to separate that atom, to actually get it to split apart so that I can liberate the energy inside the atom. And we know it would more than likely be most of it in the form of the kinetic energy of the fission fragments if I can get it to split apart. Very, very key. Binding energy per nucleon, peaking at around iron 56. In your book, it'll just say somewhere around 60, but it actually peaks at 26 iron 56. The most abundant by mass isotope on Earth is 26 iron 56 by mass. By atom, there's more 6 carbon 12 atoms on Earth, but by mass, there's more iron